Okay, transpose of a matrix. Okay, shall we? Transpose of a matrix. Are you able to hear?
Yes, I can hear you.
Okay, transpose of a matrix. What is transpose of a matrix? A is any matrix. For any matrix, transpose exists. A is any matrix. Any matrix. Okay, of any order. Then transpose. Then transpose like this, transpose of A is represented like this, represented by A dash, like this, A dash, A dash. And it is what it is interchanging rows into columns. Interchanging rows into columns. Simple. Okay, so for example, 1, 2, 3, 4, 5, 6. This is of what order?
3 into 2. 3 by 2.
Yes. So now, if this is, let's say, A. Then what? A transpose, you know. What is A transpose? You have to interchange rows into columns, no? Yes, sir. No, 1, 2. This is row, no? This row you have to interchange.
Yes, sir.
And then 3, 4.
3, 4.
5, 6. Very simple. And this becomes 2 by 3.
2 by 3. Yes, sir. Got it.
Oh, like that. That's all. I think this is simple transpose of a matrix. And then properties, its properties. Properties, what are its properties you see? See, first one, if you do A transpose, O transpose. See, this is A transpose, no? If you do transpose again, what you get? You are going to get the same thing. Yes, sir. So therefore,
yes.
A transpose, O transpose is A itself. Second one, see, A plus B whole transpose. What you get A plus B whole transpose? After, see, first you add, then you transpose. Or you transpose and then you add. It's the same thing. Yes or no? See, very simple to understand. Here you are adding first element to, see, you are adding corresponding elements. No? In rows you are adding, then after that, rows become column. No? Or columns becomes rows. Yes or no?
Yes, sir.
So then, so first you add and then you do transpose, and then you do.
We'll get the same answer.
Same thing. So the next A minus B whole transpose is A transpose minus B transpose.
B transpose.
Because it's very simple, because addition and subtraction is simply it's based on what? Based on? Simply based on corresponding elements. No, adding corresponding elements. Therefore, you get the same thing. There will be no problem. But this is what you should know. What is that? AB whole transpose is what you know.
It's not equal to.
Not equal to A transpose to B transpose, but B transpose to A transpose. This is what you get.
So can we do an example for the fourth one?
We should do and check. Then we'll understand. Okay, then fifth, the last one. K is a scalar or a real number. Real number, scalar is same. K whole transpose is K into A transpose. K is a constant. Okay, if you first multiply a constant and then you do transpose, or first you do transpose, then multiply K, it's the same thing, because here multiplying means what? Here multiplying each entry with K. With each entry you are multiplying with K, right?
Yes, sir.
Right.
So we get the same answer in the ending.
Yes. All right. So let's take an example. A is 1, 2, 3, 4. B is wanted, I am taking 1, 2. No, 1, 3 or 1, 4. 4, 3. Let's take 4 and okay.
Yes, sir.
So here A trans first one, I need not. First one is done. Second one, actually second one here we can't do because A plus B doesn't exist.
Yes, sir. Even A minus B doesn't exist.
Because A plus
Corresponding element, the second A1, 2, it's not there for B.
yeah, so if it, that means what? If at all A plus B exists, then only we can talk about A plus B transpose, right?
Yes, sir.
So this is second and third we need not even do also. If at all we want to prove, then we have to take another example. Okay, then we have to prove fourth. Wantedly, I'm taking this so that we can prove AB volt transpose equal to B transpose, A transpose. Now you tell. So now you tell. Prove. How do you prove it? AB, first AB. Can you tell me AB directly?
Yes, sir. So AB is equal to 1 into 4 plus 1 into 3.
No.
The first.
1 into 4
Sorry,
plus?
1 into 4 plus 2 into 3.
This entire row we multiply with entire column.
Entire column. Yes.
So then entire row you have to multiply with next column, then you get next element, yes or no? But
yes, sir.
This element won't be because here
it's not there. Yes.
Yeah. Okay. The next second row.
3 into 4 plus 4 into 3.
3 fourths, 12 plus 4 plus 12. So
12.
this is
Yes.
4 plus 6, 10. AB. AB transpose. What is AB transpose?
24 and 10 and 10 and 24 in the same row.
Okay. 10, 20. And this is 2 by 1. This is 1 by 2. Now B transpose, A transpose. What is B transpose? 4, 3.
4, 3. Yes, sir.
What is A transpose? 1, 3, 2, 4. Right?
Yes, sir.
Or 1, 2, 3. Right. Now we can do this 1 by 2. This is
2 by 2.
We can do this. What you get?
So 4 into 1 plus 3 into 3.
This row we have to multiply this column. Yes, 4.
Sorry, 4 into 1 plus 3 into 2.
4 into 1, 4 plus 3 into 2, 6. This entire row multiply the entire column. First row, first column element. This
first row, second column. So 4 into 3 plus?
First row is here. Second column is here. Yeah. 4 is 12.
12 plus 12.
Yes, so this is 10. This one you are going to get, don't cancel this like this. So 1 by 2. See, this is AB volt transpose. So what?
Yes, sir. Same answer.
AB volt transpose equal to B transpose to A transpose. This one theoretically also you can prove. This is not with example we prove, but theoretically we can prove also. Theoretically we can prove also. Okay, that proves we will do that. Okay. And then next we see 1, 2, 3, 4. No? So then we see K volt transpose. Okay. So
yes,
this is like
so, but it's going to be the same answer only, right? Because this is also the same as addition and subtraction.
Yes. So see, very simple. Now K you multiplying here. K volt transpose. Both are same. Very simple. We need not check that.
Yes, sir.
Okay, this is transpose and its properties. Okay, transpose means what? You have to interchange rows and columns. Or if you change rows into columns, columns becomes automatically rows. Yes, sir. This row
yes, sir.
is a column, right? Column. Automatically column becomes what? Columns become rows. That means what? Interchange of rows into columns or columns into rows. Any one thing can do. Okay?
Yes, sir.
All right. So, okay, then we'll go to next. Some theorems. Some theorems are this result is important, right? Theorems are results. So in this number one. A plus A transpose is always a symmetric matrix. Oh, I should first tell this. Okay, we'll tell some more types of this before this. So, now, some more types of matrices. Types of matrices. Some more types of matrices, in which first one is number one, symmetric matrices. Symmetric matrix. What is the symmetric matrix? See, if at all A transpose equal to A for any matrix A. Okay, A is any matrix such that A transpose is A only. If you do after transpose also you are getting A. So for example, 1, 2, 2, 1. And this is A. Then you
Yes.
then you do A transpose, you do what you get? 1, 2. This 1.
2, 1 again.
Yeah, exactly. So A transpose equal to A. A transpose equal
Yes, sir.
to A. Therefore, this what you can say, this A is symmetric. Or another way you can say is symmetric, Symmetric, say for example, this square is always symmetric. Symmetric along diagonal also. Symmetric along diagonal. Yes or no? Yes or no?
Yes, sir.
Put this two.
Yes.
So this is also like that only. This element, if you fold like this element comes here, this element comes here.
Yes, sir.
Okay. All right.
Yes, sir.
Symmetric matrix. A transpose. If at all A transpose is A, then A is simply symmetric matrix. If A transpose is A for any matrix A, then A is called
Symmetric.
symmetric. Simple as that. The next, skew symmetry. So what is this skew symmetric? Okay, for any matrix A, if at all A transpose is minus A, then A is called skew symmetry. Okay, this is clear. Skew symmetric, symmetric matrix. If at all A transpose is minus A, then A is called skew symmetric. Very simple. Or this one you can say what, or you can say A transpose plus A equal to 0. This and this both are same, sir? No?
Yes, sir.
Okay, so I'll give another example. One example I'll give. Okay, A equal to, let's say, 1, 0, 2, minus 2, 0. A transpose, you do A transpose. What do you get A transpose?
0, minus 2 in the first row and
0 minus 2. Yes, 0 minus 2. This row become column. This column.
And then 2 and 0 in the next row.
Okay, right. And this you take,
yes.
Minus you take common. Minus if you take common, what you get? Minus 0.
0, 2, minus 2 and 0.
It's minus 8. Sum.
Yes, sir.
A transpose equal to minus A is what? Therefore, what you can say is skew symmetric.
Yes, sir.
Right. So now let's go. And okay, another one I would like to show you 3 by 3 will take A equal. I would like to take like this. I want to tell you this 1, 2, 3. This is trick. This trick. I'm teaching you how to find out. You want to give an example for symmetric. See how do you give symmetric. First 1, 2, 3 you should write. Okay, this one is doesn't matter whatever it is. This diagonal.
Yes, sir.
Right. Then here, whatever comes here the same thing should come. Whatever comes here, same thing should come here. Whatever comes here, same thing should come here. For example, this in this no, you kept this one as 5. This one must be 5.
5.
And this one is 6. Then this one must be 6. This one is 8. This one must be 8. You understand? When you fold, this 5 comes here, this 6 comes here, this 8 comes here. What about 1, 2, 3? Doesn't matter.
Yes, sir.
So now you do A transpose. We do A transpose once. And 1, 5, 6 you write row. This row you write 1, 5, 6 column. Then 5 to 8 you write column. This 5 to 8. 5 to 8. Then next 6, 8, 3 and
Yes, sir.
8,
6, 8, 3.
And what is this A transpose? Same.
Yes, I got it.
So therefore, 1, 2, 3 doesn't matter. This diagonal can be anything, but this 5, if here it's 5, here it's 5, then here it must be 5. If this is 6, then this must be 6, right? This must be 6. If this is 8, this must be 8. Okay, because when you fold, this comes here, this comes here, this comes here. That's what is symmetry. So no.
Yes, sir.
All right. So then we go to next. How do you, very important note, very important note. Now let's say A is any matrix. Let's take 3 by 3. A11, A12, A13. Any matrix, A21, A22, A23. A31, A32, A32. Okay, now let's say let A is skew symmetric. Consider A skew symmetric. Not any matrix, skew symmetric. Skew symmetric matrix. Then what should happen, A transpose should be equal to minus A, A transpose.
Yes, sir.
A11, A12, A13. Yes, sir. This row I.
Yes, sir.
A21, A22, A23. A31, A32, A33.
So you're labeling it wrong, no?
No. This is 1, 1, 1. This is row I wrote column. This I wrote column. This wrote I column.
Yes, sir. Yes, sir. Now, sorry.
3, 1, 3, 2. Oh, what's it?
So it's 3, 2, no?
Oh, 3, 1. Oh, sorry. A1, 1.
8, 2, 8, 2, 3.
Sorry, correct one. A1, 3. This is 1 I have gone. Okay, 2, 3. Correct one. This A1, 1, A1.
Yes, sir. After that, it's right.
Yeah, correct. So this is A transpose. Minus A, what is minus A? Minus A11, minus A12, minus A13, minus A21, minus A22, minus A23, minus A31, minus A32, minus A3. And this both, this A is a skew symmetric matrix, our assumption. That A is skew symmetric matrix. Then what do you get? Like this, na? Yes or no?
So it's still the second and third elements in the first matrix are still, it's A1, 2 and A1, 3, right?
1, 2, 1, 3. So what?
No, so it's supposed to be in the row, no? A1, 1, A1, 2, A1, 3.
No, A transpose we did, no?
Oh, yes, now I got it.
Yeah. The
I
assumption is A is a skew symmetric matrix. That's our assumption. So
yes,
A
I
transpose
understood.
equal to minus A. Then what you get? What is a then you know what happens here? A11 equal to minus A11, hai na? This is this
Yes, sir.
must be equal to this. Yes or no?
Yes, sir.
So then, and one more thing I would like to say, this must be equal to this yes or no? A
Yes, sir.
equal to minus A22. And similarly, diagonal element A
Same
minus
here.
A33. So this is 2A11 equal to 0. A11 is 0. Similarly, this is A22. This is possible only this is 0. Yes or no? What element is
Yes, sir.
2 equal to minus 2 is not possible. Yes or no?
Yes, it's only possible if it's 0.
Yeah. So, like that. So essentially that means, therefore, what is the most important note? Okay, in skew symmetric matrix, tell me, in skew symmetric matrix, what you can say?
The principal diagonal elements are 0.
Very good. Principal diagonal elements are on 0. Number one. Number two is, okay, these are zeros. Number two is, this element is negative of this element.
Yes, sir. So the same thing that we applied for the first theorem. But over here, those two were the same. Here it's a minus sign.
Yeah, exactly. So now you should be able to give an example. That's the reason we did. You should be able to give an example so easily. That's A is skew symmetric matrix. See, how do you write? First of all,
Principal diagonal is 0, 0, 0.
yeah, this is 2. This is 3. Let's say. This must be minus 2.
Minus 2.
This is 0. This is, let's say, minus
4 or 5. Yes, sir.
whatever we want. But this is minus 3. This is 4. Minus 4 means this must be 4. This must be 0. And this is what
Yes, sir.
now is skew symmetric. Simple thing is that the 2, 3, minus 4 we have taken. 2, then this is minus 2. This is 3, then minus 3. This is minus 4, this is minus half, minus 4.
Yes, sir.
Skew symmetric matrix always. Okay. So general. So okay, A equal to 0. I'm going to write this one. Okay, let's write A, B, C. A, B. This is minus A, 0, C. Minus B, minus C, 0. Is skew symmetric. Okay? Yes, sir?
Yes. Yes, sir.
All right. Okay. Now we finished. What is symmetric? What is skew symmetric? You understood, I think, right? If A equal to, we saw what is transpose, and based on transpose, we define two matrices. One is symmetric matrix, and one is skew symmetric matrix. Symmetric means A transpose equal to A, then it's symmetric. Skew symmetric means A transpose equal to minus A, then it's called skew symmetric. Okay, then
Yes.
we understood how to write symmetric and how to write skew symmetric matrices. So skew symmetric means if it is 2, this is minus 2. This must be zeros. Okay, how do you write symmetric matrix? For symmetric matrix, diagonal elements can be anything. But the non-diagonal elements should be in symmetry. 5 means 5, 6 means 6, 8 means 8. Okay, that's what we say. Symmetric matrix, then diagonal elements must be zeros. Other elements are, now we understood. Okay, now we'll take theorem 1. Theorem 1 or result 1. Okay, what is that? for any matrix A plus A transpose is a symmetric matrix. You understood? Huh? For any matrix A, you take any matrix A, you do A plus A transpose. It's a symmetric matrix. You understand? Another way of finding symmetric matrix is this. You take any matrix, then you do A plus A transpose. Then that is symmetric matrix.
Yes, sir, got it.
Okay, but here one thing if you observe, but what all examples we saw, this symmetric matrix is discussed only for square matrix. Yes, sir. Symmetric
Yes, sir.
matrix is only for square matrix.
Yeah,
There,
because the principal diagonal is essential in all of these.
yeah, exactly. But here if you understand, for symmetric or skew symmetric, A must be square matrix. Symmetric or skew symmetric. Okay, A must be square matrix.
A square matrix.
Okay, right? So
Yes, sir.
how
Can
do
I
you
come back
prove?
in a minute?
Yeah, sure.
Yes, sir. 1 minute.
No problem. Okay. Okay, this is B
Yes, sir.
transpose. Or you can take B transpose. B transpose is A plus A transpose or transpose. So then is A transpose plus A transpose or transpose. Then that is A transpose or transpose is A. Then this is B itself. So B transpose equal to B, na? So what you can conclude? B transpose. This is any matrix B, then its transpose is same thing.
Yes, sir.
Or you can say, for A plus A transpose, this is our matrix. It's transpose. You do this transpose. A plus A transpose is A. Okay, this is A plus A transpose only, na? Simple, as simple.
Yes.
A plus A transpose. B you need not take, just for our understanding we are taking. Otherwise, if you do transpose, you are getting the same thing.
Yes, sir.
So simple. Therefore, this is always. Therefore, what is the conclusion? A plus A transpose is always symmetric. Note. A is any square matrix. Then K times A plus A transpose is always
Symmetric.
always a symmetric. K, even if you multiply K also, no problem. Yes, sir?
Yes, sir.
Okay, then next, theorem 2. No, A is, let, here A is any square matrix. Then A minus A transpose is a skew symmetric matrix. This is what is next.
So here also then K into A minus A transport.
Yes, that's true. But this theorem we have to prove. Then how do you prove? Can you prove this one? Yeah, how do you prove this one?
So for proving this,
Like previous one only you can tell. Tell me. What you should assume? Better we assume that way than
A plus.
A minus.
So can we take B only otherwise?
Yeah, B only. Let B equal to A minus A transpose.
A minus A transpose, yes.
Now B transpose equal to
then
minus
B transpose is equal to
B transpose equal to
A transpose minus A.
O transpose. Yeah. So
Yes, sir.
A transpose minus A transpose
minus
O transpose. This
This
is
is equal to A transpose minus
minus
A.
A. Which is equal to minus, you take
B
A minus
minus.
A transpose. Minus B. Simple. B transpose
Yes.
minus. Therefore, B is skew symmetric. Okay.
Yes, sir.
Okay, all right. So, okay, this is very simple. Therefore, also note what you can write.
So same thing, only K over there. K
Also,
into
K times A minus A transpose.
this is Q symmetric
Always,
matrix.
always skew symmetric matrix. Okay, this is next result. Right, very simple, no?
Yes, sir.
Then next we'll go to next we see that. So, this is important one. Every matrix means square matrices. Every square matrix. Every square matrix A can be, every square matrix A can be expressed as sum of symmetric and skew symmetric. Sum of symmetric and skew symmetric matrix. Every matrix can be expressed as sum of symmetric and skew
Q symmetric matrix.
matrices. See, that is very simple, no? Proof. Okay, proof. What is a symmetric matrix? You know, A plus A transpose, always symmetric, right?
Yes, sir.
Symmetric. Okay, here A minus A transpose is always skew
Q
symmetric.
symmetric.
Now, A I should express as sum of these two. What I should multiply here, I should add these two. If I add, what I am getting? If I add these two, what I am getting?
A 2A.
2A I am getting, but what I should get?
A.
A I should get. No, A I should express as. So what is
Yes, sir.
what we should do then? By 2. Hannah?
Yes, sir.
So then what we should do? A equal to half of, because this is symmetric, means this is also symmetric, na? Is symmetric.
Yes, sir.
Half
This is
of
symmetric. Half
A
of that
plus
will
A
also be
plus
symmetric.
oh yes. This is half of A minus A.
A minus A.
This is also symmetric. Therefore, half of A plus A transpose plus half of A minus A transpose. Very simple, no? Every matrix can be expressed as like this. Every matrix A can be expressed as sum of symmetric matrix. This is symmetric matrix. This is skew symmetric matrix. Very important result. Many problems, many different model problems we can form based on just a simple plan. This looks very simple, but its application is very tricky. It can be very tricky. So we should learn this next. Okay.
Yes. Yes, sir.
Then we will go to the problems. Okay, transpose, this transpose definition, properties of transpose, this one. Okay, AB over transpose, B transpose into A transpose. Here I would like to say one more thing is that A, B, C over transpose is what you know, C transpose, B transpose, A transpose. Okay, this idea
Yes.
is also. Why? Because A, B into C है ना, A, B, C all transpose कर दो. C transpose into A, B all transpose है ना. This is one matrix and this is another matrix. AB, if you do AB, you are going to get another matrix. Here, this whole AB considers one matrix. Then AB, C all transpose, C transpose into AB transpose है ना.
Yes, sir.
So what you can write in AB all transpose? What you can write? B transpose, A transpose. Yes or no?
Yes, sir.
Yes, so you can that thing you should understand. Okay, is that clear?
Yes, sir.
Sir, clear. We have done with this properties, and here you examples. You always do these examples for clarity. So you gave an example and you explained all these facts. And then AB all transposes, B transpose, A transpose. This we have done. Symmetric and skew symmetric matrices. What is that symmetric and skew symmetric matrix? You know that is what is that? A transpose is A, then it is symmetric.
Yes, sir.
What? A transpose is minus
Symmetric A transpose is minus A.
A transpose is minus A. Here, therefore, here you prove. So diagonal ones must be proved. Well, zeros you prove immediately. E minus E, F minus F, G minus G. We know this. Theorem A. Theorem, first theorem. What we learned first theorem? What is the first theorem we learned? Yeah, what is first theorem? For any square matrix
A
A,
plus A transpose is
A
equal
plus A
to
transpose
symmetric.
is always symmetric.
Yes, sir.
Always, it is always symmetric matrix. And A minus A transpose is a skew symmetric matrix.
Symmetric.
Yes. Okay. All right.
Yes, sir.
That also will prove. Okay. Now, so any square matrix can be expressed as sum of a symmetric and skew symmetric matrix.
Symmetric.
Yes, sir.
Yes, sir.
So here examples. Again, this examples. And then this exercise is based on transpose. See, find the transpose of each of the following matrices. First question. Okay, all that only. So next, for any matrix A, verify A plus A transpose symmetric, A minus A transpose skew symmetric. The fact which you learned. Okay, find this when A is this, and express following as symmetric and skew symmetric matrix. This you should take A. You know how to do, right?
Yes, I'll try doing these. If I have it out, I'll ask.
Yes. Okay. Right. Right. Then next topic is elementary operation, transformation of matrix. Okay.